The purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and compare measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. In this lab, we used a magnetometer app to measure the magnetic field due to a permanent dipole magnet. The measurement of the magnetic field obtained is not the only magnetic field in the environment. The Earth's magnetic field will also be present and will superimpose with the bar magnet's magnetic field to produce a net magnetic field. The experimental design needs to compensate for the presence of the Earth's magnetic field. This is done by ensuring that the magnetic field of the bar magnet is orthogonal to the Earth's magnetic field so that it can be measured separately. To find the magnetometer on the phone, I oriented the meter stick in the east to west position. Then I placed the magnet on the end and moved the phone along it. I marked the spot on the phone with tape at the location with the greatest X component. Then I rotated the phone and repeated the process for the Y component. Here are some visual aids to help explain this method. Here are details that were observed while I was doing this. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the X direction. As the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. Here are the main physics properties involved in this lab and their respective equations shown. For the Biot-Savart law, data is plotted in a graph and the value for n is found. For the magnetic field of a dipole, the value for the magnetic dipole moment was calculated using this equation. Next, I found the distance from the magnet to the located sensor, which produces the X component of the magnetic field of 5 different values. These are shown on the left side of each table. After getting the X component of the magnetic field as close to this value as I could, I recorded the X component in the distance from the magnetometer to the magnet. In order to get the most accurate results, I completed 3 trials for each of these measurements and calculated the average data. These averages are shown in the table on the right. The data recorded previously can be used to calculate the distance dependence. However, plotting these values directly will produce a curve, making it difficult to find the true value. To make this easier, I plotted the natural log of the magnetic field and distance from the calculations and determined the value for n. The graph and equations are shown. By creating this graph, we were able to identify the slope in the equation as a value for n. Here are the equations explaining this process. N was found to be negative 2.5497. The equations explaining the calculations are shown here. The value for k was calculated to be 1.102 times 10 to the negative 6. We can then use this next equation by plugging in k to find mu, the dipole moment. Mu was calculated to be 5.512 ampere meters squared. The final step of this experiment was to measure the off-axis magnetic field. This was done by finding the distance from the magnet to the magnetometer that creates a magnetic field with an X component of 0 and total magnitude 100 microteslas. This distance was represented as d perp, and we moved the phone from the horizontal ruler this distance as well. This puts the sensor distance d from the magnet as shown in the visual aids here. Next, using Excel, we entered in d perp measurements from 3 trials and calculated the average total distance d. Components for the magnetic field at these distances were entered, and Earth's magnetic field was subtracted from the y component in order to calculate the corrected y value. D-perp. Next, I was able to create a representation of the magnetic field of the dipole using code. First, I used a function to calculate the magnetic field vector. I then created 6 different observation locations from which to measure the magnetic field. After running the code, the model above was produced. The white cylinder represents the bar magnet, the orange arrows represent the magnetic field on axis, the blue arrows represent the magnetic field off axis, and the pink arrow represents the field at 45 degrees from axis. The magnetic field at 45 degrees was calculated to be the following vector, and the magnitude was calculated to be 0.02344 teslas. Since the magnetometer is affected by the magnetic field from the Earth, this would affect the observations and results. It must be accounted for when taking measurements. Values in mu and k would be inaccurate. The magnetic field magnitude would increase about 2 times, but the direction would stay the same.